Welcome back to my stats course. What we talked about last time is the definitions of statistics such as data, sample, population, variable. Right now, what we're going to do is talk about sampling methods. So the first thing we need to cover when talking about sampling methods is random, biased, and what that does to the statistics and the inferences that we're going to make. So the first thing we need to understand, if I get rid of Z and P here, and I erase my information about what an individual is, what I'm going to do is I'm going to say, how can I get a random sample of Y? So one way I can get a random sample of Y is I can take every kth element of Y. Now, the reason why that might not be a good idea with how Y is written out is because Y is ordered and it's not randomly ordered. It's not randomly sequential. So I know I'm going to get ever increasing values of Y for every increase of K. Because I know that, I have bias in my sampling method. So another way I could do it is I have 6 numbers here. I'm going to roll a single 6-sided die, and I'm going to take whatever number pops up on the die. So in rolling my die, X 3 times, X is now going to be 5, 3, and 4. So now I've got a random sample of Y, because all I did was roll a die. This just happened to be what I got. I'm going to roll my die again, and I'm going to call this X1, and I'm going to say my X2 is going to be equal to 0, 3, 4. So by 0, that means I rolled the die at a 1. By 3, that means I rolled the die at a 4. And by 4, that means I rolled the die at a 5. And if I had rolled the die at a 6, I would have gotten 5. So this is where we have the concept of an indexing set being offset from the population set. This just happens, right? Now, what you'll see here is I have different descriptions of X1 versus X2, but my Y, my population, is fixed. It doesn't change with my sampling methods. So if Y were randomly ordered, I could take every kth element, like every other element of Y, and my subset of X would also be random. However, since Y is not, I cannot systematically sample from Y. But I can just take a simple random sample of Y using the method of the die. Another way we could do this is if we broke Y down into different partitions. So I'll say Y1 is equal to 0, 2, 4, and Y2 is equal to 1, 3, 5. And if I randomly selected Y1 or Y2, and the elements of Y1 and Y2 were random, which they're not, because you can see that they're even or odd, but that could happen randomly, then I could cluster select only one of the partitions. And that would be the cluster method of sampling. The reason why random is so important is that, let me grab a different color, is that random is the same thing as independent and identically, that wasn't supposed to be a T, distributed. Okay. The reason why independent and identically distributed is so important is that we want to talk about what's known as error. We have 2 different types of error. Let me remove this. So error can come from the sample. So for example, we saw that if X1 was equal to a new set of values, 0, 3, 4, and X2 was equal to 1, 5, 3, then let's say the average of X1 would be equal to 0 plus 3 plus 4, which is 7 divided by 3, which we'll get into how to get that later. But the mean of X2, so the measure of center of X2, is equal to 9 divided by 3, which is equal to 3. So we can see that these are not the same number, and therefore this is what we call sampling error, is that the descriptions, so sampling error, is best represented as the mean of X1 minus the mean of X2 is not equal to 0. And that's what we refer to sampling error. So we want to find out what is the distribution of that error. What's the probability of how much not 0 this number will be? The other way we can get error is from not sampling correctly. For example, you might roll the die and get the wrong number because you forgot to offset your index. So that would be human error, which is not what we can account for statistically.